Okay, so we're going to start off the neuromuscular unit by doing a little bit of review on the nervous system. We have one section where we're reviewing the nervous system, and then we'll have two where we review, the muscular system. So to start off, these are the three things that we want to go over. So we want membrane potential, action potential, and then graded potentials. Okay, so to start off, what establishes membrane potential? All right, there's four things here. Okay, so we've got, I don't even know where to start. So we've got the potassium leak channels, which cause potassium to go outside of the cell because there's a big gradient, flow down gradients, right? We've got the sodium leak channels over here. So there you go. That causes or allows sodium to go inside the cell because, again, gradients, more outside than inside. We've got proteins. Remember, these are negatively charged negatively charged particles. They can't leave the cell because they're so big, okay? And so that makes membrane potential more negative. And then we've got the pump, 3 sodium out, 2 potassium in. So the pump makes the membrane potential more negative. So I'm going to put a negative there, a negative here by leak channels. Proteins are negative. Sodium leak channels make it more positive / less negative, okay? This is our equilibrium point. So this is in a neuron, and if all other things are, everything else is closed or whatever, this is what's going on in a neuron. And so we've got a membrane potential of -70. This pump is important because if we didn't have the pump, our membrane potential would be 0. And then when we open a door because of some stimulus, nothing's going to happen because there's no gradient. So we've got our resting membrane potential of -70. How does an action potential work? So we start off here. We're at resting potential. Stimulus happens that allows membrane potential to go from -70 to at least -55. So we hit threshold. This opens up some gates. We have the sodium activation gates that open quickly. Remember, the sodium inactivation gates are already open. And then the potassium gates open slowly. As a result, we have depolarization due to a lot more sodium influx than potassium efflux. At the end of depolarization, the sodium inactivation gates close. So as a result, sodium isn't able to continue entering in the cell through those voltage-gated channels. The leak channels are still there. They're still open. They're hallways. We don't close them. But we close all these gates, and so there isn't as much sodium going in. Repolarization occurs because those potassium gates are finally open all the way, which allows a lot of potassium to leave. We end repolarization when we get back down to resting potential, and around that point, everything resets. The sodium activation and the potassium activation, we're just going to call it potassium because it's one gate, they close. The sodium inactivation reopens. But because the sodium gate closes slowly, we have hyperpolarization. So from here to here, that's due to potassium leaving the cell. That gate finally closes. The potassium gate finally closes here. And we return to resting potential. And this is due to potassium influx. Potassium comes back in through the leak channels, and it's really being pulled in by the proteins that are negatively charged. Remember, positive and negative attract, not attack. They attract each other. And so those negative proteins say, hey, come hang out with us, positive potassium. This leads into temporal and spatial summation. And this actually maybe should have gone before, but this is how we have a stimulus that can ultimately cause an action potential to occur. So we have temporal summation. This is a single neuron repeatedly sending a signal over and over. I like to think of this with my son, Asher. He doesn't care. If he wants your attention and you're doing something, he doesn't care. Now, as a parent, I've gotten pretty good at ignoring my kids on occasion. Okay, when I'm talking to my wife or doing something else, watching a football game, I know I'm a terrible person. Okay, but Asher will come up and he'll go, Dad, 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 Dad. And finally, after the 37th time, I'll go, what do you want, Asher? That's temporal summation. That's just him telling me repeatedly he needs my help or something. And then we've got spatial summation. I think of this as when we go to a concert or go to a football game or whatever we used to do when we didn't have this distance, right? So imagine that you're at a football game or something and you're there with a group of friends. And let's say you decide to go, I'll go get popcorn or whatever for everybody. And then you're looking for your seat and you can't find your seat. Well, one person yells, one of your friends yells, and you don't hear them because it's a stadium and there's lots of people, right? But so what happens is all four of your friends yell at the same time to get your attention. And that, you're over here to my left. That's spatial summation. So when spatial summation, you have multiple neurons sending a signal at the exact same time to a different neuron. Okay? So the other thing is you can have temporal and spatial summation, and the way this would work would be your group of friends keep yelling your name until you finally hear them. Okay? So temporal is one neuron sending one signal repeatedly. Spatial is lots of neurons sending one signal at the same time. And temporal and spatial would be multiple neurons sending signals repeatedly. And with these graded potentials, they can either be hyperpolarizing or depolarizing. Hyperpolarizing or inhibitory, they do something that causes membrane potential to become more negative. Depolarizing or excitatory, they cause membrane potential to become less negative, get us closer to threshold. Okay. It's also important to know that it takes several neurons to activate a different neuron. So it's not as one neuron, it doesn't have a strong enough power or ability to activate cause and action potential in a second neuron. It usually takes, they estimate, between at least 40, I think is the number I last heard. And that's how our nervous system review is going to end.